Hello one and all, welcome to another online video by Einstein Academy. In this video, we'll be looking at learning outcomes F, G, and H from the topic of atomic structure from the JCH2 chemistry syllabus. Learning outcomes F says that candidates should be able to describe the number and relative energies of the s, p, and d orbitals for the principal quantum numbers 1, 2, and 3, and also for the 4s and 4p orbitals. Learning outcomes G says that students should be able to describe the shapes of s, p, and d orbitals. Finally, learning outcomes H is to be able to state the electronic configuration of atoms and ions given the proton number and charge. So if all this looks very alien to you, fret not, because this is something that will be very new to you if it's the first time any one of you students is approaching this topic. So if you were to follow me closely for the next few minutes, you should be able to learn enough to be able to answer these learning outcomes. So let me begin with giving a brief overview of what we're trying to learn in this part of the topic. So previously, we had this model of the atom, whereby you have the nucleus, and in the nucleus is the protons and the neutrons. And we say that basically the electrons is revolving around the nucleus. However, this is a bit of a lie because we cannot really view the electron as a particle that is going in either a circular orbit or an elliptical orbit around the nucleus, just like the planets revolve about the sun. This is really by far not an accurate picture of how electrons behave around the nucleus. In fact, if we were to say that the electron has a fixed path of movement around the nucleus, it will actually violate the Heisenberg uncertainty principle, which is one of the fundamental principles of the area called quantum mechanics. So in this part of the learning outcome, we actually would like to study more accurately the behavior of electrons around the nucleus. So the behavior of electrons and protons and neutrons, and for the matter of things that are very, very small, falls in the domain of quantum mechanics. And Erwin Schrödinger, a famous Austrian scientist, famously discovered this equation, whereby if you solve the equation for any given microscopic system, you would actually describe the electrons, the protons, and neutrons, or whatever small particles at non-relativistic energies. Basically, when the movement of the particles are not close to the speed of light. The speed of the particles is not close to the speed of light. So if we were to solve this equation for the hydrogen atom, we would use a set of atomic orbitals, which would give a more accurate description of the behavior of the electrons around the nucleus. And we will also be able to solve for the energy levels of the different types of atomic orbitals. So what are atomic orbitals? Basically, when we say that the electron cannot orbit in a fixed path around the nucleus, what we actually are only able to say is, like, for example, if this is the nucleus, we are only able to say that, like, for example, what is the probability of finding an electron in this given region of space? This is the only thing that quantum mechanics allows us to describe the electron. We are not able to say how it's actually moving, but we are only able to say what is the probability of finding the electron within this given region of space. And atomic orbital, the solution from the Schrödinger equation, precisely gives us that. Basically, what is the probability of being able to find electrons in given different regions of space? And typically, the meaning of an atomic orbital is such that we draw a shape such that within the shape, there is a 98% chance of finding the particular electron within the space. And associated with each atomic orbital, there is a fixed energy level. These things will become clearer when we look at the shapes of the orbital, and I'll be able to explain them in greater detail. Now, each atomic orbital is labeled by 4 different quantum numbers. And out of these 4 quantum numbers, the one that you have to pay most attention to is basically almost likely the principal quantum number, because this is the one that will be used most in answering of questions. The other 3 is not so commonly used in the answering of questions, but I will still explain what they basically represent. Okay, so on to the first principal quantum number, on to the first quantum number, which is called the principal quantum number. The principal quantum number is denoted by n, and is the first quantum number of an atomic orbital. And orbitals with different principal quantum numbers are of different energy levels. So the way that you should think about principal quantum number is basically their energy levels. So if I were to draw an axis, a y-axis, and I put an E here, basically like at the bottom will be the lowest energy atomic orbitals, and at the top will be the highest energy atomic orbitals. At the bottom level, you have energy level 1, and in this level, there will be a certain number of atomic orbitals where electrons can reside. And then when you go to energy level 2, there will be another set of atomic orbitals that can hold electrons. And when you go to n equals to 3, another set of orbitals, and n equals to 4, so on and so forth. For the purpose of the A-level syllabus, the highest we will go until is the energy level 4. Okay, so the higher the value of n, the greater the energy of the shell, as I've drawn here. N equals to 1 is the lowest energy, while n equals to 4 is the highest energy. And hopefully it's intuitive to you that if we were to put electrons into this orbital, we would prioritize putting the electrons into first the lowest energy orbital. We will put it in here first. And when these orbitals are filled, then we will start to put energy into the next highest energy orbital. Okay, so once again, view the principal quantum number as the energy level. The lower the energy level, the lower the energy of the atomic orbital, and these orbitals will have priority in filling electrons up. The azimuthal quantum number. So previously we also mentioned that the electrons revolve in a circular orbit, but this is not true. In fact, not all shapes of orbitals are spherical in shape. And basically the azimuthal quantum number, which is given by the symbol L, basically describes the shapes of the orbitals. When L is equals to 0, we have the S subshell, and the shape of the S subshell, as we will see later, is indeed a sphere. There is no angular momentum because the spherical shape has no angular momentum, has no direction to the orbital. On the other hand, if L is equals to 1, we will give rise to the shape of the P subshell, and later, as we will see, the shape of the P subshell is in the form of a dumbbell shape. Okay, so basically L controls the shapes of the orbital, whether is it a sphere, is it a dumbbell, or if it's in the D subshell, the orbitals are in the shape of a clover leaf, as seen like this. And there's also one type of D orbital, which has a dumbbell, and then it has a donut shape in the middle. Okay, so basically the azimuthal quantum number controls the shape of the orbitals, whether is it a sphere, whether is it in a dumbbell shape, or whether is it in a cloverleaf shape or in this special shape. The magnetic quantum number, on the other hand, tells us how many number of orbitals are contained within each subshell. So if you were to solve for the Schrödinger equation, if you were to see the whole solution, when L equals to 0, the magnetic quantum number can vary from 0 to 0 only, which means that there is only one and only one S subshell, which looks like a sphere. If L is equals to 1, that corresponds to the P subshell, which, as we have mentioned, looks like a shape of a dumbbell shape. But when L is equals to 1, the ML can actually range from -1, 0 to +1, which means that there is exactly 3 orbitals that form one set of P subshell. So basically, the way you can think about magnetic quantum number is that it tells you how many orbitals are there in one set of a particular subshell. As we will see later, the P subshell has 3 orbitals, 3 P orbitals. One of them will point along the x-axis, one of them will point along the y-axis, and one of them will point along the z-axis. Okay, so 3 P orbitals form a set of P subshell. And for D, if the L quantum number is 2, which corresponds to the D subshell, the ML can range from -2, -1, 0, +1, and +2, which gives us a total of 5 orbitals that make up a set of D subshell. This will become clearer as we start to see the shapes of the orbitals in the next few slides. The spin quantum number, on the other hand, tells us the intrinsic angular momentum of the electron. So let me briefly talk about the history of this. It was previously thought that if the electron was like a top, and then if you put an axis, that basically the electron is like spinning spinning in one direction, like a spinning top. But the thing is that for any spinning top, the electron, or any top for the matter, can either spin in the clockwise direction or the anti-clockwise direction. And experiments have shown that this intrinsic quantum number can take on two values, which is either plus half or minus half, which led people to think that perhaps the electron was really like a spinning top, then that it can actually spin in the clockwise direction or in the anti-clockwise direction. However, if you were to perform calculations to calculate the speed at which the electron is spinning like a top, you will arrive at the answer that is faster than the speed of light, which is prohibited by Einstein's special theory of relativity. As such, we now know that the electron is not really spinning like a top, but since experiments show that there is really intrinsic angular momentum of the electron, we just call it the intrinsic angular momentum without really knowing where the intrinsic momentum comes from. But we do know that for sure that this intrinsic angular momentum can take on two values, which is either plus half or minus half. And as we will see later, basically it corresponds to either spin up corresponds to either the spin up state or the spin down state. And this, again, I just want to emphasize again that this is just the intrinsic angular momentum, which we actually do not really understand where it comes from, but we know that it exists due to experimental facts. In this diagram, we meet the shapes of the orbitals for the first time properly drawn in a nice pictorial view. So the s orbitals is in the shape of a sphere, as I've mentioned before. So as you can see here, when n equals to 1, in the first energy level, there is only the s orbital, because like if you look at all the other orbitals, the n is not equals to 1, which means that if I were to draw an energy level diagram, and why do I want to draw the energy level diagram? The reason is because I want to know which atomic orbital is in the lowest energy state, so that when I fill in the electrons, I will put it in accordingly first to the orbitals of the lowest energy. So when n is equals to 1, which is the lowest energy level, I actually have the 1s subshell and the 1s subshell only. And again, I like to remind you, like the shape of the 1s orbital looks like a sphere, as seen here. When we go to the n equals to 2 energy level, we will again have an s orbital, but in this case, it will be labeled as the 2s orbital because the first number is always the principal quantum number of the atomic orbital. The 2s orbital is also in the shape of a sphere. However, this is actually bigger than the 2s atomic orbital is bigger in size than the 1s atomic orbital. Shape-wise, is still the same. It's still in the shape of a sphere. At n equals to 2, however, if you were to look here, n equals to 2, the p orbitals also come into play. And as we have mentioned before, the magnetic quantum number actually tells us that 3 p orbitals form a set of the p subshell. One of the p orbitals will lie along the z-axis, as you can see here, is directly along the z-axis. This p orbital lies directly along the y-axis and it's called the py orbital. So let me label this. This is called the pz orbital. This is called the py orbital because it lies along the y-axis, and this is called the px orbital because it lies along the x-axis. So at the n equals to a 2 energy level, not only is there the 2s atomic orbital, there is also a set of 3 p orbitals. When I say 3 p orbitals, I mean there's 3 of them, but the thing is that the number in front of it should be energy level 2, which corresponds to the principal quantum number 2. So I'm drawing 3 lines here to indicate that there are 3 p orbitals, one along the x-axis, one along the y-axis, and one along the z-axis, and the shapes look like a dumbbell shape. Now, if we were to go to a top energy level 3, we would see that there is again a s orbital. And again, the s orbital is in the shape of a sphere, but again, this size will be bigger than that of the 2s orbital as well as the 1s orbital. At energy level 3, there will also be a set of 3 p orbitals. And this again is in the shape of a dumbbell shape that lies along the px, py, and pz orbital. However, when we get to the energy level 3, the principal quantum number 3, there is a set of d orbitals that look in the shape of a cloverleaf pattern. And the cloverleaf pattern, it's as I've drawn before, that looks like this. Okay, and the differences is in the way that they lie along the axis for these 4 orbitals. So if you were to look at this diagram, the orbital actually lie in between the x and the y axis, and as such, this orbital will be labeled as the dxy orbital. This will be labeled as the dyz orbital because it lies between the y and z axis. Sorry, this is the dxz orbital. Because this is the dxz orbital because it lies in between the x-axis and the z-axis. This, on the other hand, lies between the y and z-axis and therefore is the dyz orbital. This set of orbitals lies directly along the y and the x-axis, and the notation for this set of orbital is the dx squared minus y squared orbital. So again, let me try to differentiate between this 3 and this one. This one, the orbitals lies directly along the y-axis and along the x-axis. So you can see they are along these 2 lines. However, this orbitals is in between for the dxy orbital, it's in between the x-axis and the y-axis. It's not directly along those lines. So if I were to draw a clearer view, if this was the x-axis, this was the y-axis, the orbitals will actually lie in between the x and the y-axis in the form of a cloverleaf pattern. So this is the dxy orbital. Okay, this 3 lies along the x and y, x and z, and y and z respectively, while this directly lies along the x and y axis. This orbital, on the other hand, lies along the z-axis and looks in the shape of a dumbbell shape, but the only difference is that there is like a donut shape that is in the middle of this atomic orbital. And this is labeled as the dz squared orbital. So just to remind you again, an atomic orbital is basically a given drawn shape, either a sphere, a dumbbell shape, a cloverleaf shape, or this shape. And basically within this shape drawn, there is a 98% chance of finding an electron within that given region of space. And the energy levels of these orbitals will tell us how we were to fill in the number of electrons into each different atomic orbital later. Okay, so we would like to talk about the relative energies of the orbitals as I have drawn here. And the reason, like I said again, is to figure out why we want to figure out the relative energies of the orbitals is so that when we fill in electrons, we know that we are supposed to put in electrons to first the lowest energy orbital before we slowly fill it up to the higher energy orbitals. So this is basically the relative energy of the orbitals, and you can see at level 1, the principal quantum number 1, there's only the s orbital. At the principal quantum number 2, there is the s orbital and the p orbital. At principal quantum number 3, there is the s orbital, the p orbital, and the d orbital. However, notice that when you go to the principal quantum number 4, there is the s orbital, p orbital, d orbital, and the f orbital. But if you look at the relative energies, you will notice that this 4s orbital is actually lower in energy than the 3d orbital, which means that if you were to fill in electrons all the way until the p orbitals, the next electrons that will fill in will go into the s orbital instead of the d orbitals. I'll explain to you this more clearly in the later slide, so just hang on to me. Okay, so first of all, we would like to talk about how we can get the relative energies of the orbitals, because as you can see, right, it's not always true that the s orbital is lower in energy than the p or the d, and it's not even true that for the principal quantum number 3, the energy of the orbitals is always lower than that in the principal quantum number 4. So the answer to figuring out the relative energies of the orbitals actually is hidden in the periodic table. So let me explain how do you get these relative energies from the periodic table. So if you look at the periodic table, you can think of this as n equals to 1 row, n equals to 2 row, n equals to 3 row, and n equals to 4 rho. Okay, and then this block is basically the s orbital. This block, you view it as the p orbital, and this block, you'll view it as the d orbital. So the way that you read this periodic table is from top to bottom and left to right. So if you go from top to bottom, principal quantum number 1, so the lowest energy orbital will be the 1s orbital. Although the hydrogen and helium is placed in these regions, but for the purpose of this discussion, let's just think of the hydrogen and helium as being placed in this region. So the lowest energy orbital is the 1s orbital. Then you go to the next row. Then the next lowest energy orbital will be the 2s. And then left to right, then the 2p, then the 3s, then the 3p, then the 4s. Notice that it naturally gives the answer to the fact that the energy of the 4s orbital is in fact lower than the 3d. Because only after you finish the 4s, then you hit the 3d orbital. I understand that if you go by this notation, this should actually read 4d, but just know that the first set of d orbitals actually appear in the principal quantum number 3. So I just like to point out that for the d orbital here, this is actually, although it is row 4, but it's actually the 3d orbitals. And then after the 3d orbitals, it is the 4p orbitals. As you can see here, after the 3d, it's the 4p. Okay, so let me just again, for clarity's sake, write out everything. If I were to draw again this energy level diagram, the lowest energy orbital is 1s. Okay, so 1s is only one line because there's only one orbital. And then after that, I'll go to 2 and it'll be 2s. And then after that, left to right, 2p. And remember that the p orbitals exist as a set of 3. So 3 2p orbitals, and then 3s, and then 3p, and then after that, 4s, followed by here, which is the d orbital, 3d. And remember the 3d orbitals come in a set of 5, so 1, 2, 3, 4, 5, before going to the 4p orbital. And the 4p orbital, there's a set of 3. And you can convince yourself the way that you read this periodic table will give you the correct relative energy of the orbitals. You can just double check with this part. It will give you the answers even if you work out all the way until principal quantum numbers 4, 5, or 6, so on and so forth. Okay, so that's to figure out the relative energies of the orbitals from the periodic table, and it's important. Let's say now we have 4 electrons that we want to fill up. So I would also like to mention at this point that basically each orbital can fill 2 electrons, and when you put the electrons, they must be of opposite spin. So I'll put 1 electron in here because the electron will first go into the lowest energy orbital. And if I have another electron, I will fill into the next lowest energy orbital, which is again the 1s, but the electron must go in with the opposite spin. Then I will fill in the next electron, the next electron, the next electron. And now if I have one more electron to fill, I will have a dilemma in the sense that I can either choose to put the electrons into this, like this, separately, or I can choose to pair it up like this. So there's a choice for me to make. And the answer is that I should fill it up like that and not like that. Okay, and more to talk about this in the next few slides. But basically, the most important thing is to first figure out the relative energy of the orbitals, because only then can you decide to fill in the electrons into which lowest energy orbital first. Okay, so electronic configuration is the arrangement of electrons of an atom or molecule into their shells. So basically filling up the electrons in the different subshells. And it's constructed from three principles, which is the Aufbau principle, the Pauli exclusion principle, and also the Hund's rule. So the Aufbau principle basically says that an electron is added into the orbitals in the order of increasing energy from lowest to highest energy. And this is basically what I've been emphasizing from the start of the lecture. You fill it up from the bottom up in terms of energy-wise. The Pauli exclusion principle states that no two electrons can have the exact same set of quantum numbers. What this simply means is that if you were to place electrons in the same set of orbitals, such as the 2s, and one of them is spin up, the other one must be spin down, you cannot place the electrons such that they are of the same spin, because this will violate the Pauli exclusion principle, because these two electrons will have the exact same set of quantum numbers. Okay, as an example, I'm just going to show this. Like for example, this up electron, you can say that n is equals to 2 because the principal quantum number is 2. The L is equals to 0 because it's the s orbital, and the ML is equals to 0, but the MS will be equals to plus half. For this spin down electron, everything is the same. N equals to 2, L equals to 0, ML is equals to 0, and the MS is equals to minus half. And therefore, these two electrons will not have the exact same set of quantum number because of the MS spin quantum number. However, for this case, both electrons will have the exact same set of quantum numbers, which will basically violate the Pauli exclusion principle, since it states that no two electrons can have the exact same set of quantum numbers. Hund's rule says that each orbital in a subshell is singly occupied with one electron before any one orbital is doubly occupied, and all electrons in singly occupied orbitals have the same spin. So briefly, what it means is what I've discussed just now. If I have a set of 3p orbitals, let's say this is in 2p, the energy level 2, principal number, quantum number 2. If I were to fill in one electron, I would definitely put it in like that. The second electron, as I've discussed, there is a choice. Either I can pair it up like that, or I can put them in separate orbitals. And which one do I choose? The answer is given by the Hund's rule. Each orbital in a subshell is first singly occupied with one electron before any other orbital is doubly occupied. So in this case, they must be singly occupied first before it's doubly occupied. So I know that this is not the correct way to fill up the electrons. And moreover, when I fill up the electrons, there's actually in fact one more way to fill it up, because I can have another case whereby although when I fill it up separately, I actually put one spin up and put one spin down. Okay, again, this is not the right way, because it says that all electrons in singly occupied orbitals must have the same spin. So I will put them both spin up. And the reason for this is that if I were to put the electrons in the same orbital, paired electrons in the same orbital are on average closer to one another. And because both electrons are negatively charged, they will actually experience a greater repulsion, and that will lead to the destabilization of the atom. So we prefer this way because the energy will be lower as compared to this case, because it will experience greater repulsion. Same for this. This will actually also experience greater repulsion. And as such, pairing electrons in the same orbital is energetically unfavorable. Okay, so let's practice how we can use those three principles to finally build the whole electronic configurations of various atoms and ions. And this will basically wrap up the whole chapter. So again, the lowest energy orbital is the 1s orbital, followed by 2s, and followed by 2p. So I've been doing this for a while, but if you can't figure out these energy levels, then just go back to the periodic table to get these relative energies, as what I've gone through in the previous slides. So nitrogen is 714, which means that it has 7 protons and 7 electrons since it's electrically neutral, which means that I have to fill up 7 electrons. Based on the Aufbau principle, I will put the first electron in the lowest energy, and then the next one is still the lowest energy orbital, and I'll put it into the 1s orbital, but it must be of the opposite spin so that it satisfies Pauli exclusion principle. The next one will go into here, and the next one will go into here, filling up 4 electrons. Then 1 electron, I'll put it in here. So now I will have 5, but I still need to put in 2 more. The next one, I do not pair it up because that would violate Hund's rule. So I'll put it in this case with the same spin. And then the next final one with the same spin, which will be like that. And the way we write this notation is that since there's 2 electrons in the 1s orbital, this will be 1s2. Then there is 2 electrons in the s orbital, so this is 2s2. And then there is 3 electrons in the p orbital, which means it's 2p3. So basically, this is the electronic configuration of the nitrogen atom. Okay, all this is what I've explained so far. The Aufbau principle, the first electron is added into the 1s orbital, second into the 1s. Then by Pauli exclusion principle, the spin of this second electron must be opposite to that of the first electron. Then after that, we'll fill the third electron in the 2s orbital, the fourth electron in also to the 2s orbital but of opposite spin. Then the fifth electron into the 2p orbital of the next lowest energy, and then the sixth. And the sixth electron must be singly occupied and of the same spin with the first electron. And then the 7. Now if we were to look at the oxygen atom, same thing, 1s, 2s, and 2p. So oxygen has 8 protons and 8 electrons. So 1, 2, 3, 4, 5, 6, 7. Now the 8th electron, we got no choice but to pair it up. And hence we will pair it up in this way, but it must be of the opposite spin, so that again it satisfies Pauli exclusion principle. So this is the electronic configuration for oxygen. And in simple notation, it's just like this. 2 electrons in the 1s orbital, 2 electrons in the 2s orbital, and 4 electrons in the 2p orbital. For the fluoride ion has 9 protons, but since it's negatively charged, it has 1 more electron than proton, which is 10 electrons. Number of electrons is 10. So again, 1s, 2s, and 2p, 10 electrons to fill, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's the electronic configuration of the fluoride ion. And in simple notation, 1s2, 2s2, 2p6, because there are 2 electrons in the 1s orbital, 2 electrons in the 2s orbital, and 6 electrons in the 2p orbital. Okay, so far we have talked about constructing electronic configurations for atoms as well as for anions. Now we would like to talk a bit about the electronic configurations of cations. And to deduce the electronic configuration of cations, we first start out by writing out the electronic configuration of the corresponding atom, and then based on the charge, we will remove the appropriate number of electrons from the highest energy orbital. So let me clarify this with an example. So for example, if you want to deduce the electronic configuration of the Na plus ion, so sodium has an electronic configuration of 1s2, 2s2, 2p6, and 3s1. This is the electronic configuration of the sodium atom. But since it is 1 plus charge, we know that we have to remove 1 electron from the highest energy orbital. And which electron is in the highest energy orbital? It will be the electron in the 3s orbital, and hence we remove this electron, which will give rise to an electronic configuration of the remaining, which is 1s2, 2s2, 2p6. And this will be the resultant electronic configuration of the Na plus ion. Okay, the last part of this chapter, I would just like to talk about electronic configuration of the first row D block atoms. So again, if we go back to the relative energies, one s will be at the bottom, and then followed by 2s, and then followed by 2p, and then followed by 3s, and then 3p, and then 4s, and then 3d. Again, this can be gotten by reading the periodic table. So when we go to scandium, whereby there are 21 electrons, I would feel 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 here, 13, 14, 15, 16, 17, 18, 19, 20, and 21. Notice that the 4s orbital is actually filled before the 3d orbitals are filled. And that is just because of the fact that the relative energies of the 4s orbital is actually lower than that of the 3d orbital. So you can see that the electronic configuration for scandium is 4s2, 3d1. Then for titanium is 4s2, 3d2. Then 4s2, 3d3. Okay, so if we were to fill up one more for the chromium, we would expect the electronic configuration to be in fact 4s2, 3d4, because it should be the electronic configuration for chromium. But as you can see here in this table, the electronic configuration of chromium is actually written to be 4s1, 3d5, which means that we actually promoted an electron from here to up here. Okay, I'll explain this anomaly. This is basically an anomaly in the electronic configuration of transition metals. And there are basically two anomalies in such electronic configurations of the transition metals, which is basically chromium as well as copper. Now, if we were to fill in one more electron, we would fill it in this way, and this will be 4s2, 3d5, which is the electronic configuration of manganese. Then 4s2, 3d6 for iron. 4s2, 3d7 for cobalt. Four s2, 3d7 for cobalt. 4s2, 3d8 for nickel. And also 4s1, 3d10 for copper. So again, we will expect the electronic configuration for copper to be 4s2, 3d9. However, again, we will promote an electron from the 4s orbital into the 3d orbital, hence giving an electronic configuration of 4s1, 3d10 for the electronic configuration of copper. So this is the second anomaly for the electronic configuration of the transition metals. Finally, for zinc, it will be 4s2, 3d10. So let me now explain about the two anomalies for the electronic configuration of the transition metals. So for the chromium, the electronic configuration should be written as 4s1, 3d5. So I'd just like to point to you the fact of this argon. So sometimes we write this to basically simplify the electronic configuration, and this will basically represent the electronic configuration of argon. If you were to look at the periodic table for argon, it's here with 18 electrons. Which means the electronic configuration for the argon can just simply be also 1s2, 2s2, 2p6, 3s2, 3p6. 6 plus 2 is 8, 8 plus 16 is 14, 16 and 18, which is 18 electrons. So the way we write it like that with a square brackets and argon, this just represents the electronic configuration of argon, which is exactly this. It's just that we are lazy to write it out. And moreover, all the chemistry actually happens to the valence electrons. So we're not really interested in the inner shell electrons. And if we're lazy, we can just write this notation. Of course, if the questions ask you to write out the full electronic configuration, then you better make sure to write it out in this entire form. Okay, so as we've mentioned previously, we would expect the electronic configuration of chromium to be 4s1, 3d5, we would expect it to be 4s2, 3d4 because the 4s orbital is below and then the 3d orbital is on top. So if we were to fill in 1, 2, 3, 4, 5, 6, we would expect it to be filled like that. However, it actually prefers to promote an electron up from the 4s orbital into this orbital, which is the 3d orbital. And the official reasoning given is that if you have a state whereby the 3d orbitals is half filled, the electronic configuration is particularly stable. And if they were to ask you for reasoning, I guess this would be the reasoning that you would give at the A-level standard. However, this is not a really true explanation, because if you were to go to the next period, which is tungsten, the electronic configuration of tungsten is actually 6s25d4. And if this explanation was really true, then we would actually want to promote an electron from the 6s orbital into the 5d orbital to give a half-filled set of 5d orbitals. But since tungsten is not true, there is no really simple explanation for this, except kind of like just remember that the electronic configuration for chromium is 4s13d5 instead. So basically, in order to remember this, just remember that there are two anomalies in filling the electronic configuration for transition metals, and they are in the form of chromium as well as copper. And is that when you are able to promote an electron from the lowest 4s orbital into a higher energy 3d orbital to achieve a half-filled d orbital or a fully filled d orbital, the atom will prefer to do so. And that is why officially that chromium has an electronic configuration of 4s13d5, because it prefers to have a half-filled d orbital instead of 4s23d4. Copper is the same thing. Instead of it being 4s, you would expect it to be this case: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You would expect it to be like that, 4s2, 3d9. However, if I'm able to promote an electron from the 4s into the 3d, I would get an electronic configuration whereby the 3d orbitals is fully filled. So again, if it's able to get a half-filled d orbital or fully filled d orbital, the official reasoning is that fully filled d orbitals and half-filled d orbitals is particularly stable. So it prefers to be in these electronic configurations. Okay, so I will also need to talk about anomalies in the electronic configuration of transition metal cations. So previously we mentioned, in order to get the electronic configuration of cations, we first have to write out the ground state atomic electronic configuration. So for example, for scandium, the SC, right, it will be, again, just argon, and then 4s2, 3d1. Okay, so now when we want to, because of the fact that scandium is 3+, I'm going to remove 3 electrons. But the question is, do I remove the electron from the 3d orbital, or do I remove it from the 4s orbital? So when you fill up the atomic configuration, electronic configuration for the atoms, you will fill up the 4s orbital first, because if you were to read off the periodic table, you will realize that the relative energies of the 4s and the 3d orbitals is such that the 4s orbital is lower in energy. And that's why we fill up the 4s orbital first before the 3d. Now, when we remove electrons, we would also remove from the 4s orbital first. Okay, so this is just a rule that you have to follow when you remove electrons from transition metals. So for transition metals, when you're filling up electrons, we fill up the 4s first, and if we are removing electrons, we also remove from 4s first. Okay, as an example, if we were to look at Ti+, the electronic configuration is Ar followed by 4s2, 3d2. But because it's 1+ charge, so we have to remove 1 electron. And as we have said here, if we are removing electrons, we will remove from the 4s first. So we will remove 1 electron from the 4s, and the resultant will be 4s1, 3d2. If we have to remove 1 more electron, we also remove from the 4s, which means that the electronic configuration will have no more electrons in the 4s orbital, but it will just be 3d2. If I were to pick another example, like say chromium 3+, let's say the electronic configuration of first the atom for chromium is 4s1 3d5, one of the anomalies as we have talked about just now. We are going to remove 3 electrons, which means we will first remove 1 electron from the 4s orbital. Then the next electron we'll remove is from the 3d, so it will become 3d4. Then we'll remove 1 more electron, will be 3d3. So the electronic configuration will just be 3d3. However, if it was Cr plus and we only remove 1 electron, then we'll remove from the 4s orbital and the resultant electronic configuration will just be 3d5. Okay, so highlight again for transition metals. When you're filling electrons, you fill into the 4s orbital first. And when you're removing electrons, you remove from the 4s orbitals also first. So I'm just going to leave you with the list of the electronic configurations of all the transition metal ions. Give it a go to see if you can really get the correct electronic configuration as indicated in this column. Okay, so that sums up learning outcomes F, G, and H. And let me just go through the learning outcomes to make sure that we properly understand what we need to know from this part of the topic. Describe the number and relative energies of the s, p, and d orbitals for the principal quantum numbers 1, 2, and 3, and also for the 4s and 4p orbitals. So this part of the learning outcome is basically to be able to do this, right? In terms of energy, the lowest is 1s, then 2s, then 2p, then 3s, then 3p, 4s, 3d, then 4p. So all the way until the 4s and 4p orbitals, which is here. Be able to deduce this, and again, I remind you, you can get this information by just knowing how to read it off the periodic table. Describe the shapes of the s, p, and d orbitals. So the s orbital looks like a sphere. The p orbital is in the shape of a dumbbell, but I just remind you again, for the p orbitals, it comes as a set of 3. 1 along the px orbital, 1 along the py orbital, and 1 along the pz orbital. The shape of the d orbital, on the other hand, comes in 2 different shapes. One of them is a cloverleaf pattern, while the dz square orbital is a dumbbell with a donut shape that's in the middle. Okay. State the electronic configuration of atoms and ions given the proton number and charge is what I've discussed in the last part. Basically, write out the electronic configuration of different atoms. So again, like for example, fluorine, 1s2, 2s2, and 2p5. Okay, whereas for F minus, because it gains 1 electron, so when you fill up the next electron, you will go into the p orbital, so it's 2p6. Okay, hopefully you have gotten out all the things that you need to get for these learning outcomes. As this lecture is quite long, I'm going to leave the questions for these learning outcomes on to the next video. So stay tuned for the next video as we will start to talk about the questions from the past year A level that will be testing you particularly on these 3 learning outcomes. So if you like this video, just hit the like and subscribe button, and I will see you for the next video. Thank you very much and see you next time.